studies section in the advanced lighting training section. The purpose of this section is to examine a number of photographs that I've taken over the course of several years and attempt to analyze and understand the quality of light and shadow. When we're talking about the quality of light and shadow in the real world, it's crucial to understand this to create a real artist's perception of light and shadow in the world, so that when we're using our CG tools, we can understand when we're looking at it what it is about it that doesn't look right. I'm sure many times you put in lighting that you thought should work in your scene, and when you rendered the image, looked at it and went, yeah, you know, it's just not right. I'm not really sure what's going on there, but I'm having trouble putting my finger on it. Hopefully by the time we get to the end of this section, you'll have a more sophisticated eye for the quality of light and shadow, and will be able to look at your image and analyze that a little bit better. And then once you're familiar with all the tools, hopefully implement a really good sound solution. So to begin with, I've taken a series of pictures of a simple white coffee cup on a simple white surface. And the reason I did that is I wanted the environment to be simple enough that we can clearly see exactly what's going on here without the mess of additional textures, colors, and shapes. It's a nice simple shape, nice simple materials. So in this image, it's very easy to see that we have a single object on a ground plane, and it's illuminated by 3 light sources. We know that because we can very easily count 1, 2, 3 shadows. 1, 2, 3 shadows, which means 3 light sources. Additionally, we can tell the approximate position of these light sources from each other. It looks like they're in a line because the shadows go approximately in a line. So 1, 2, 3 up above here somewhere. They're almost overhead because there's not much of an angle between the lip of the cup and the edge of the shadow. And one additional thing is that we can tell by looking at this that the light sources are either very small or very distant. And the way we can tell that is by looking at the quality of the shadow edge. The shadow edge is very sharp. It's not completely sharp, but it's quite sharp. As a matter of fact, if we look at it very closely, we can see that where the shadow is very close to the cup, it's much sharper than in areas where the shadow is actually farther from the cup. And this is a common feature of all shadows. All shadows are sharp where they touch the object that's casting the shadow, and get softer as they're further away. The smaller the light is, the more difficult that is to see, because the softness is much smaller. And we'll see that a little further as we go along. So what we can tell about these light sources is that they're either very small or very distant. And the reason it's small or distant is because distance obviously makes objects seem smaller in perspective. They're not actually smaller, but the lines of perspective coming from them are narrower. Therefore, a light in the distance seems smaller. The most obvious example of this is the sun. The sun is obviously many times larger than the Earth, but it appears smaller to us because it's very distant. In the same way, if these were very large light sources, but very distant, they would create sharp shadows. In this case, the actuality is we look at this image and we realize that these are probably incandescent light sources, and they're probably on the ceiling or close by. An incandescent light source, by the way, is a light source that creates light through heat. So candle, common household light bulbs, tungsten halogen lights, and so forth. Another thing that's interesting about this image is the way the 3 lights are illuminating the ground plane. Obviously out here where the light is fairly even, all 3 lights are contributing light to this area. But if you look, this is slightly grayed, and that's because the cup is occluding this area from one of the light sources, and this area as well, and this area as well. Therefore, only 2 of the lights are getting to this area, and this area, and this area. Next area is actually occluding or shadowing from 2 of the light sources, and also this area here and this area here. So only 1 light is illuminating those areas because of the occlusion of the cup or shadowing. And this center area is not getting any direct light from any of the three light sources. Therefore, it's darker. The only light that's getting in there is indirect light from the room. Indirect light is also sometimes called ambient light, or irradiance, or radiosity, or bounced light. And we can also see lots of bounced light going on the inside of the cup as well. Okay, so that about covers this cup. Oh, except there's one more interesting thing. If we look into the reflections, because this is a glazed cup, we can actually see the light sources reflected. So there's 3 in a row. Only catch 2 of them here, and 2. Oh, here's 3. 1, 2, 3. The third one must just be out of view here. Okay, so that's it for this image. Moving on to the next image, same cup, same image plane, but obviously a vastly different lighting scenario. What's happened here is I've taken the white plane and I put it up next to a window, and outside it's a cloudy gray day. So what we're receiving here is light from the sky. So this is all skylight, no sunlight. A very interesting thing that's going on here is these shadows. Okay. So once again, we notice that the shadows are sharp, right where the shadow begins to be cast, right where the object casting the shadow touches the object receiving the shadow. And as it gets further off, it very quickly diffuses into a soft shadow. Okay. The reason why this one becomes soft very quickly is because the light source is very large. We're talking about the sky here, and in fact the sky is even larger than the light that's getting here, because this is coming through a window frame in the background, so we're only seeing part of the sky. So if this were under the whole sky, the shadow would be so soft you might not even notice it very much. So this is a portion of the sky coming in through a window frame, and we're seeing that it's vastly softened. And the interesting thing is you can see it's softened in this direction as well. So the light, which is larger than the cup, is wrapping around the cup and diffusing into soft shadows. And here's where we get into a discussion of umbra and penumbra. The umbra is the area where no shadow or no light is being received from the light source, and that's, you can clearly see it in this V here. The penumbra is this area. It's where there is partial light from the light source. And then outside of that is the fully illuminated area. Okay, so there's 2 major differences between this and the previous image. The previous image had 3 light sources, 3 small incandescent light bulbs. This one has 1 light source, skylight coming in through a window frame. And the result is that there's 1 shadow cast, which is this very soft shadow with the umbra. And this shadow is much softer than the other one. And it's much softer because the light source is much larger. Here's another image of our cup on a plane. This one was taken under a fluorescent light source. Fluorescent light source is different from an incandescent light source in a number of ways. It doesn't produce light through heat. It produces light by getting particles of gas to fluoresce in a tube. What's particularly interesting about this image is because the fluorescent light is in a long tube, it's had a very unusual effect on the quality of the shadow. We can notice here, and for your information, you can actually see in the reflection here, there's actually 2 tubes and they're going across this way. And even if we didn't see the fluorescent light reflected in here, we could know that just by looking at the quality of the shadow. The reason we could know that is because if we look at the shadow, we notice that it's very soft crossways, but it's sharper up and down. In this direction, you can especially see it here, where this shadow is fairly sharp going in this axis, but in this axis you can see it's much softer. This is blurred right out here. Okay, and the reason that has happened is because the fluorescent light is quite large in one axis and quite narrow in the other axis. So because the light is large along this axis, the shadow is soft crossways. And because the light is a tube and it's very narrow in this axis, the shadow is much sharper in this axis. So line lights or linear lights or very narrow rectangular area lights will tend to create this type of shadow. Although line or linear lights have a fundamental problem, and that is that this shadow will be completely sharp, which is an error. In the real world, there's no such thing as a one-dimensional light source. And we talk about this in detail elsewhere, but just to cover it again, all light sources have three-dimensional volume. All real light sources. There's no such thing as a point light or a line light or a, for example, two-dimensional area light. Point lights have no dimension. Linear lights have one dimension. Area lights have two dimensions. Those light types don't exist in the real world. We use them in CG because they tend to help us improve our render times, and that's a very valid use for them. But be aware that there are good times to use these lights and there are bad times to use them. Okay, but that's covered in much detail elsewhere. The interesting thing is knowing that the kind of thing that you see with a linear light actually occurs in nature. All right, here again we have fluorescent lights. Now the interesting thing about this compared to the previous image, I'll just go back to the previous image, is you may see a really different color shift. One of the reasons for this is that this fluorescent light has glass color in it to bring it into a warmer color range, a more natural color range. But a lot of cheaper or older fluorescent light bulbs you'll see will create this greenish cast. So if you're ever doing a lighting design and you need to create a really hardcore fluorescent light look, you might consider pushing your lights slightly into the green range. People do tend to respond to slightly green light as being obviously fluorescent. Okay, so there's a particularly interesting thing about this. Although it's a fluorescent light source, we see that there's multiple shadows. So this indicates to us that this isn't a single light source. If there are multiple shadows, there must be multiple light sources. This particular light is one of those light fixtures in the ceiling that has three screw-in light bulb type fluorescent lights, those kind of curly ones. And it's covered by a frosted glass bowl. So the frosted glass bowl kind of munges together the light from the three lights, but if you look at the glass light bowl directly, you'll see you can see three bright spots on the glass bowl, and those three bright spots are actually acting as independent light sources, but they're softened together by the glass bowl, so you get these multiple shadows that are kind of partially munged together, and then you get this kind of a green cast. Okay, now take a moment for your eyes to adjust to the light of this image. This is an image taken in candlelight. This has a number of interesting features to it. First of all, we can tell by seeing 1, 2, 3 shadows that there are 3 candles illuminating this light. We also note that the candlelight is much dimmer than the other light. I deliberately exposed it this way because I wanted to take the previous images and this image under the same exposure to show you that there is a vastly different intensity between candlelight and skylight and fluorescent light, incandescent light. We tend to light scenes by putting our lights at 100% and turning them on and illuminating them well without the basic understanding that there is a vast difference in exposure between, for example, the natural light of skylight and sunlight and the interior light of puny little lights like our household light bulbs and even punier candles. I'm sure you've been inside on a summer day in a dark room and walked out and had to close your eyes or put on sunglasses because it was so bright it was almost painful on your retina. Well, what happens is your irises have to close down, reduce the amount of light that gets in before you're able to look at that image comfortably. And the same when you're outside on a bright sunny day and you walk into a house that's not well illuminated, maybe the lights are off. Everything seems pitch black at first. You have to stop and wait. Your irises open up to allow more light in. It's very important to understand that there are orders of magnitude of difference in brightness between something like candlelight and something like sunlight. And the reason why we're able to look at a room illuminated by candlelight and see things, and we're also able to look outside when it's sunny and see things, is because our eyes adjust to allow more or less light in. This is very important to understand if you intend to be a serious lighting artist, because there are times when the overexposure of, for example, sunlight coming into a room in through a window is very crucial to the image looking right, or where the underexposure of having, for example, looking into a room from outside is very important. If you, for example, decide to do the inner room with sunlight coming in the window, and the sunlight coming in is about the same brightness as the illumination from light bulbs in the room, then your image will never look right. There needs to be a really serious difference between those two light sources, or your image will never look and feel right. Okay, so take a look at this image. I'm going to switch to a photo of this with the candles in it. Here we go. Look at these overexposures. Okay, what's happening here is that these candles, which are actually, the flame is actually yellow, but the light coming off the candles is so bright that this image is clipped at white, which means it's the maximum amount of color that this monitor can display. Okay, there's more light coming out of this candle than this monitor can display, so these just turn into white, clipped, overexposed areas. There's a little bit of detail in there. Understanding this overexposure is very important. In our global illumination section, we're going to be getting into a discussion of what a high range image is and how much more exposure exists in a high range image, and most commonly we're talking about HDR images. How much more exposure exists, how much more data exists in that image than in something like this, which is just a standard low range image, which contains pixel values in the 0 to 255 range. We need to understand that actual illumination range is much higher than that, much higher than that. And we have to pick the range of our exposure for our image. And that's covered in more detail in the global illumination section. Okay, for this image I have actually altered the image. I had to turn up the brightness and contrast a little bit just so we could see a little bit better. The exposure was really low because this is a single candle. What's interesting about this image is that this is also a candle. If we look at the previous image, let's look here, we can see that our shadows are quite sharp. And they are sharp because the candle flames are quite small light sources. Okay, see that? Nice sharp shadows. You can see that they're sharpest there, and you can actually see a little bit of fuzziness off the edge because the shadows are sharp here and get softer and softer and softer as they get further away. Okay, when we look at this image, again the shadow's sharp right here, but it immediately becomes very soft. This indicates to us that this candle must be a larger light source. Well, a candle flame is a candle flame. How can it be a larger light source? That's a very interesting question, so let's answer it. This is how. In this case, the candle flame has melted down inside the candle. I'll show you. So the candle flame is down inside the candle, and it's actually illuminating the candle wax. All right. So now the candle wax itself has become the light source, but it's much larger than just the candle flame. Therefore, the shadow is much softer. Okay, so this happens with, well, anything that takes a small light and makes it larger. If you take a small tungsten halogen light bulb and put a piece of paper in front of it, right? They actually do this trick on set. They'll put something called a diffusion gel, which is a fireproof piece of sheet of frosted plastic. They'll put it in front of a light to make a larger light source for the purpose of creating softer shadows. Using softer shadows in portrait photography, for example, is considered glamour lighting. They say it tends to take the wrinkles out of aging actresses. So it's a preferred method of photography. Whenever you're looking at photographs of older actors, have a close look at it and see if you can see any sharp shadows. In most cases, unless it's very dramatic photography and they really want to emphasize those shadows, you'll probably see that the shadows are very soft, making the skin look very smooth, even if it actually isn't, because all the small little shadows from the cracks are filled in by those very soft shadows from large light sources. And on that note, if you're ever looking at dramatic photography, you'll notice that the shadows are probably quite sharp and the contrast in the image is actually quite high. Contrast equals drama. Contrast in all its contexts, as a matter of fact, is equal to drama in imagery. Well, in all art, as a matter of fact. Okay, so we've covered a lot of bases looking at our little white cup on our little white plane. So now let's start looking at some more complex photos and see if we can identify what's going on with them. To begin with, we have this image of this door with some light coming through it. And when we're analyzing photos, we ask things like, well, what could that light source be? What's it coming from? What's the quality of the shadows? We look at this, and most people look at this image and first they go, well, it's obviously a sunny day and there's some sunlight shining through here. And that's probably true. But depending on what the exposure of the camera is, this could be a street lamp outside. We don't know. And as a matter of fact, for the purposes of the image and for the purposes of creating a lighting design, what the exact light source is isn't really relevant. What matters is understanding the qualities and properties of the light and the shadows and being able to recreate them. For example, if you're doing lighting design, somebody may give you a photographic image and say, hey, I want this light quality. You may look at it and define it as being the sun or the moon or a street lamp or a candle or whatever. What it actually is isn't as important as what it looks like. What's interesting, well, there's a number of interesting things about this image. First of all, we notice these patterns on the wall, okay? And that'll cause us to look at this glass and go, oh, okay, well, look, there's cut glass in here. So there's some kind of prismatic effect going on, which means there is some refraction of light going on. And in this case, we notice that some of the light is concentrated and other areas is less concentrated. This is a classic example of what we call in CG caustics. Light is being focused in certain areas, and that light that's being focused is being taken away from other areas, and that's the darker areas around the bright areas. So if you were to take all this light and actually average it out, you would get the actual intensity of light that's coming through here. Okay. Another interesting thing that we see is that this light is being reflected onto the back of the door here. Not just through image reflection, but light reflection as well. And let me just deal with that for a second. One of the interesting things in CG is that image reflection and light reflection are dealt with as two totally separate operations. Let's be clear that in the real world, light reflection and image reflection are exactly the same thing. Image reflection is the reflection of light. Light reflection is the reflection of light. That which we call specularity in CG, which is light highlights, in the real world, that is also merely the reflection of light. As a matter of fact, everything that you see is a reflection of light. This is one of the most classic examples of the fact that real lighting in the real world is actually very simple to understand and analyze. It's the lighting in the CG world that is very complex, and those complexities have been added for a number of reasons, the most important of which is that if we were to create rendering engines and rendering tools which only obeyed physical realities, then renders would take far too long. So we've created ways of faking the look of real light and real materials in ways that actually make renders possible. Let's see, what else do we see in here? Well, we can see that there's some different materials. We see that the door is somewhat reflective. We can sort of see the shape of this reflection here, but we look here and we see some brass, and we can see that there's more sharply defined reflections. In CG, we might say that this is irradiance or light reflection or radiosity or whatever you want to call it, and we might call this reflection. So we might say, oh, irradiance, reflection. In fact, they're the same thing. The only real difference is that this material is very, very smooth, much smoother than this material. And that's what makes the difference between a soft specular highlight and what we call a reflection. Reflective materials are simply very, very smooth. They're called, in the real world, they're called highly specular, which means highly smooth. A specular surface is a surface that is extremely smooth, like a mirror. Whereas a surface with low specularity is one that is very rough, like maybe a carpet or a wall that's painted with matte painting. If you were to take, for example, a silver-backed mirror, so your common household mirror, and a perfectly white opaque piece of paper, and put them under the same light, you could argue that both of those materials are reflecting the same amount of light. You'd say that well, in theory, they probably don't actually reflect 100% of light, but for our purposes, we'll say that a white piece of paper that's opaque reflects 100% of the light, and we'll say that a mirror reflects 100% of the light. The primary difference between a mirror and a white piece of paper is that a mirror maintains the structure of the light that hits it. So the reflected light has the same structure as the light that hits it. Whereas a piece of paper, when the light hits it, because the paper at a microscopic level is actually incredibly rough, it's made of all these different fibers, it diffuses the light out in all kinds of directions. So the real only difference in light reflection between the theoretically perfect white piece of paper and the theoretically perfect mirror is that one is very smooth and the other is very rough. Okay, moving on. This is taken at the same time. The only thing that's changed here was I've moved in a little bit with the camera, and I've changed the exposure. And the reason I changed the exposure is I wanted to demonstrate two things. I wanted to demonstrate the quality of the caustics going on here, and I wanted to show how different the exact same lighting can look under simply different exposure. Under this exposure, many of my students look at it and go, okay, well, the other one was daylight. Well, this one is now maybe a street light outside or a car headlight or something. It isn't. It is sunlight. The previous one was a sunny day. This is the same sunlight coming through the image. It's just that the camera exposure is lower, which means the camera is allowing less light in to be exposed onto the recording medium. What's interesting here is you can see very clearly how there's kind of medium light areas here, and then these are brighter, and then the areas directly around the brightest areas are even darker. So what's happening is these cut glass are acting as kind of prisms to refract the light and focus it into these areas, but that light has to come from somewhere. So it's coming from these darker areas directly around the caustic highlights. So a caustic does not add light into a scene. It takes light away from certain areas and concentrates it into other areas. So some areas become brighter, and we must also know that other areas must therefore become darker. Okay? Okay, that's enough on real-world caustics from now. Let's start looking at some outdoor lighting. Here's an image of a child inside a tent. and it's outside. And we can tell just by looking at the tent roughly what the lighting is, even though we can't directly see anything about the environment. We can see that, well, first of all, there's no direct sunlight. We know this because there aren't any really hard shadows. If there was direct sunlight, there would have to be hard shadows. We can see that there is a kind of a highlight of light, an arc here, and that corresponds with this arc. So if we looked at the top of this arc and compared it to the top of this arc, we can roughly guess what the position of the light is. So it's back behind the camera and above. In this case, it's probably the hemisphere of the sky that is on our side of the tent. If we look up here, we go, well, are we sure it's a cloudy day and not sunlight? Because we can see a little bit of sharpness to the shadow. We can see some highlights on the top of this. This seems fairly bright to be, for example, just a cloudy day. So we can surmise that probably what's going on here is that it is a cloudy day, but the clouds may be very thin. So thin that you could probably see the disk, or at least the rough shape of the sun through the clouds. When we start looking inside the tent, we also notice some interesting things. We see that the tent is blue, so we would expect all the light on the child inside the tent beyond this arc to be blue. We notice that it isn't all blue. If we start looking carefully, we can see up here there's some very yellow light, and look in the bridge of the nose here, we can see yellow light as well. So we know that up above there must be some yellow light. Probably what's going on here is that the top of the tent is made of material that's this color. It's this kind of thin nylon that's translucent. And we can see down here below that there's quite white lighting here. We can see definite highlights and shadows in the coat. We can see blue all in here, all in here. So we know that there is blue light coming in the sides, and that coincides with our knowledge that there is blue material around the sides of the tent. But we notice one more thing. If we notice in the shadows on here, we see blue light. So we say, well, there's blue light coming in from this direction. If we look on this side carefully in the shadows, we see kind of purpley red light. See in here? In here? So we must surmise that there is some red light coming from this side towards the child. If we had to recreate this in visual effects, we would need to be looking at this image closely enough to see all those very fine details that you might not at first notice when you look at the image. You might look at the image and go, oh yes, there's a child inside here. It's softly lit because the light's hitting the tent. And you might even notice this bright light on top and go, well, that's not right, that's not blue, so there must not just be blue material in this tent. The things that are difficult to notice are these details. And part of growing your artist's eye is understanding to look into the shadows, because shadows contain a great deal of information, especially about what we call the ambient light going on in the scene. And by ambient light, I don't mean CG ambient. That's a completely different animal that we'll deal with elsewhere. When I say ambient light, what I mean is non-direct light in the scene. And non-direct light means light that is diffused or reflected after it leaves the direct light. In this case, light is being diffused by this tent material. Okay, moving on. Here's another picture inside the tent. So this is getting right in there. And we see a confirmation that in fact this side of the tent has red material. And it's very obvious in this scene because we can see the side, even if we didn't see that, we see a very strong red highlight on the side, and that would give us a very strong indicator. Okay? We see it under here. Look in this shadow. Look in these shadows. Okay, that's where there's a lot of information. There's a very strong highlight here. We also see a very bright yellow highlight all over the shirt and arms in this case. And we can even see the shadow cap. We can even see the light, yellow light on top of the cap here in this highlight. An interesting thing here, and you might see it if you just look out the back here. Well, you can barely see it at the edge of the picture. Let me just move this down a little bit, is that there seems to be a mesh on the tent, and you can see bright light outside. So in fact, what's happened in this image is that the sun has come fully out from behind the clouds and is shining down on top of the tent, and the top of the tent is made of yellow material, so you have this very bright light. So now, whereas previously, in the previous image, the brightest light in the tent seemed to be this kind of blue wash because most of the material is blue. Now the brightest light is this yellow, toppy, very soft light. And we can tell that there is no direct light in here because there are no hard shadows, so there's no direct sunlight. But there is very soft yellow light because the top of the tent material is yellow, and also the top of the tent material relative to the child is very large, therefore the shadows are all very soft. This is kind of like one of those tests where you build a cube with different colors on the walls and turn on your multi-bounce lighting. But this is reality. Okay, moving on. Whenever I show this image to my classes, the first thing I ask them is, how does this image make you feel? And it's an interesting question. So take a minute and look at this image and ask yourself how it makes you feel. When I ask that in my class, most of the people respond with, well, that makes me feel really bored, or, oh, it's really drab. Occasionally people go, wow, it makes me feel bright and energetic. Most people, though, get a sense of drab and boredom from this image. And this is a very interesting question, because if we can understand what it is about this image that makes us feel bored and drab, or possibly energetic and excited, it's up to you. If you can figure those things out, then you have an actual lighting design tool, an image design tool, a composition tool that you can put into your toolkit. We look at this image and we see that it's almost monochromatic. Everything's very white. The lighting is white, the ceiling is white, the floor is white, the shelves are white. There are the products on the shelves that have a certain amount of color. So there's not a lot of really kind of bright primary color in here. Therefore, this image doesn't really excite us. All right. Now, there's many times when scenic and lighting designers need to create images that have a sense of drab and boredom. And understanding that the lack of intense color and intense contrast will create that kind of drab and boredom is a great tool. It's a great thing to know. All right. And one of the interesting questions is looking at this and understanding that this is, one of those big box stores, is asking the question, why was this done? Was this done deliberately, or was it just cheap? Was it just cheap? They had a bunch of extra white paint and these are cheap light bulbs. The answer is a little bit of both. The design intention behind this is manifold. First of all, if all your reflected light is white, it means that no matter what your product is, it'll look pretty acceptable. You wouldn't want to have a bunch of green items under kind of red warmy light, because it's going to make it darker and browner. It's going to make it feel not as nice. So, and because you're dealing with a big box store which has tens of thousands of products in it, each one which has been designed and has different colors on it, you want to do your best to try to make all those products look as good as you can. So you've decided to use a very neutral lighting arrangement. Additionally, because the floor and ceiling are white, it means that light, as much light as possible, is being reflected back and forth. That means that you can actually use fewer lights and have a better illumination. This is actually good for the electricity budget. If the ceiling was black, for example, and the floor was black, even though the same amount of lights were on, the whole room would feel much, much darker, because a lot of the light would be absorbed into the black floor and the black ceiling rather than being reflected back and forth. And thirdly, because these are large surfaces, when the light reflects onto them, they're diffusing. So the floor and ceiling are essentially becoming much larger light sources. And a large light source means softer shadows. And softer shadows means glamour lighting. So with a lot less direct light and direct hard shadows, everything, including people in the store, are going to look better. So this is actually a fairly clever lighting design, which many people may not have ever even thought of. Now here's another interesting thing in this image. If you look over on this side, you'll see that there's a slightly different color change here. The lights seem a little bit yellower. You may guess that this is the cosmetics department of the store, and you'd be correct. The reason is because human beings putting makeup on their faces want to look as good as they can, or rather the store wants them to look as good as they can. And under this kind of harsh white light, especially overhead light like this, people aren't going to look as good as they could. So over here they've put warm fluorescent lighting with diffusers all over the place to reflect the light and diffuse it as much as possible, and they've warmed it up, and that enhances human skin tones. So the cosmetic department has their own special little lighting design that will help them sell their cosmetics a little bit better. Here we have obviously a winter image, and if we look at this very closely, we'll see that the foreground lighting is a little bit cool, and then we have this really warm patch of light in the middle, and then we have kind of darkness here, and then we have this bright, snowy, kind of warm patch on the top. Now initially looking at this, you may go, no, this is white. This is white light on white snow. But that's very difficult to reconcile, because if we look at this is also snow. This is clearly not the same color as this. Either this is cooler than this light, or this light is warmer than this light, or more likely both. What has actually happened here is this is looking east, the sun is setting in the west, and it's so close to setting that it's actually coming in beneath and above a cloud that's on the horizon. So a cloud is casting this shadow, and underneath it is sunlight, and above it is sunlight. What's interesting about this is this sunlight here is really warm, almost red. The reason why it's red is because when the sun is very low on the horizon, it has to shine through a lot more atmosphere to get here. And what happens when sun shines through atmosphere is that the sunlight, which is close to white, bounces around among the oxygen and nitrogen molecules. And some of it is reflected back into space, and some of it is diffused into the sky, and some of it continues forward as direct light. Now the interesting thing about that is that certain frequencies of light are more likely to get through without being diffused through the atmosphere, and certain frequencies of light are more likely to bounce around amongst the air molecules and get diffused into the atmosphere. And if you think about that for a moment, you'll realize that the red end of the light spectrum is the one that tends to get through, and the blue end of the visible light spectrum is the one that tends to get diffused into the sky. This is actually why the sky is blue, because the atmosphere is stripping out a whole bunch of the blue light from the sunlight and allowing the warmer light to get through. And this opens actually a very interesting discussion, and this is about light color. Many artists spend a good deal of their career with the unfortunate misunderstanding that light is white, that most or all light is white, unless it's, for example, a pink neon sign. Well, that's not the case. All light is colored. Everything that you see is emitting colored light towards you. If you're in a room with a blue wall, then you know that blue light is coming towards you. If you are standing next to a yellow sign, then you know that yellow light is coming towards you. Everything that you look at that has color means that that color of light is coming towards you. And skylight and sunlight are no different. Skylight and sunlight are two components of the original light that comes from the sun. They've been split apart. And when you take the close to white light of the sun and you strip a bunch of blue light out of it, what you're left with is red and green light. Because, of course, the primary colors of light are red, green, and blue. When you remove blue, you're left with red and green. Well, there's still some blue light in there, but because some of the blue light has been stripped out of sunlight to make the blue sky, what you're left with is yellow, or amber light as we call it. And this is manifest here, where you can see the skylight shining down on here, creating this area which is cool because the sunlight can no longer reach this area. And then you look in here, and especially up here, this is a really good example because the snow is white. This color is a little bit deceiving because the sunlight is mixing with the color of the trees and so forth. But if you look up here where the snow is white, you can truly see the color of the sunlight, and you can see how yellow it is. So if we were to take the yellow of the sunlight and the blue of the skylight and mix them back together, we'd have something that is close to white light. And the interesting thing is that on a clear sunny day where you can see the blue sky and the sunlight, and you look around and you go, well, yeah, but everything looks like it's lit by white light. Well, it is. Because the blue light, for example, if you're looking at a car on the road, the blue light of the sky is shining on that car, and so is the direct light of the sunlight. So they're actually mixing back together onto the car. The place to see the blue light is in the shadows, where the sunlight is not shining. And we'll look at some pictures that demonstrate that a little bit later. Now there's one more interesting thing. If you look across the street at this house, you can see in the window there's a light on here. Inside that house, this room is lit by a normal household light bulb. And this is where I'd like to start the discussion of Kelvin color temperature. Kelvin color temperature is the light scale that's used to measure natural light. For example, blue skylight is in the 10 to 40,000 degree Kelvin range. Sunlight is in the around 5,000 degree Kelvin range. And incandescent light bulbs are in the 2,800 to 3,200 degree Kelvin range. And Kelvin temperature comes from incandescent. So if you take a piece of iron and you heat it up, when it first starts to heat up, you'll see that it's a kind of a dull red, and then it'll heat up to kind of a red, and then a bright orange, and then to a yellow, and then to a white. And if you were able to heat it up even more and it didn't melt, it would actually start to emit blue light. Okay, so the Kelvin color temperature is taken from, well, if we heated this up to a certain temperature, it emits this color of light. All right, and the interesting thing is, actually, here's an aesthetic point. We think of red and orange and yellow as warmer colors, and we think of the blue end of the spectrum as cooler colors, and it's because we associate red and orange and yellow with fire, and we associate, blue, the colors of blues, with water and ice and cold things. So we think of the blue end of the spectrum as cool, and we think of the red end of the spectrum as warm. Whereas in fact, the physical reality is that the red end of the spectrum is much cooler than the blue end of the spectrum. That physical fact doesn't matter. What matters to us is our perception and understanding, which comes from, the million years of human evolution and our experience with fire and ice and water. So what really matters in imagery is what it feels like. But it's important to have a physical understanding of what's going on behind the light. So when you compare this light, if you were in this room, you would probably think, wow, there's pretty white light in here. But when you're able to stand back and look at it in the scale of a world that's illuminated by blue skylight and amber sunlight, you're able to compare those and see how vastly different the light of a normal household incandescent light is compared with skylight and sunlight. It's much warmer. much warmer looking, and therefore much cooler in the Kelvin color temperature scale. Okay, here's another outdoor image. It's a slightly different look. This image is fairly bright. It's outdoors, but we can also see that the shadows are fairly soft. Not entirely soft, but fairly soft. We can see in the distance that the exposure back here, especially in this section, is a little overexposed, whereas the foreground here is fairly well exposed. So what we can gather from this, and actually if we look along this fence, we can see there's areas of better exposure on the fence. And this may be a shadow coming from this tree. So we can gather that this is a day that has some clouds in the sky, but there may be thinner and thicker areas of clouds, and there may even be bits where the sun is actually poking out. And if we're clever, we can actually look into the reflection of this car, and we can see that there's along the edge some bits of blue sky. So we can tell in this scenario that there are some clouds in the sky, and that at this particular moment in this area there's a probably fairly thin cloud in front of the sun. Okay, another outdoor image, another very clearly cloudy day. In this image we actually get to see the sky, and then the clouds are fairly thick. Now what's remarkable about this image is not what we've previously discussed before, which is that there's a large overcast sky, therefore all the shadows are very soft. What's remarkable about this is if you look, the color of the foliage in the foreground is incredibly vibrant. You wouldn't normally expect this. On a sunny day, these colors don't actually seem this vibrant. Now what's happened is, above this cloud, there is blue skylight and amber sunlight, which would normally on a sunny day be hitting this. And we get, fairly high contrast, dark shadows and direct light and highlight and so forth. But what's happening is the cloud is acting as a great big filter, and it's taking all that sunlight and all that skylights, all that amber light and all that blue light, it's mixing it back together, it's diffusing it all back together. So what's coming out the bottom of the cloud is actual sunlight colored light, which is close to white. Okay, so the light is close to white. Question is, well, what do you mean? It's obviously it's gray light. It's not white light, it's gray light. Well, that's partially true. All gray light really is less white light. Because these clouds are not totally transparent, they're translucent. It means that a lot of the light that's hitting the clouds is actually bouncing back into space. And depending on how thick the cloud is, more light. For thicker clouds, more light will be bouncing back into space. For thinner clouds, less light is bouncing back into space. And this is why thinner clouds look brighter and thicker clouds look darker. It's because less light is getting through. It's just a thicker layer to try to get through. But the interesting thing is that the light is so close to real natural sunlight that these colors actually become more vibrant under an overcast, cloudy day like this. Okay, here's one of our direct sunlight images. This image is quite interesting for a number of reasons. First of all, we can look at it and immediately say, okay, yeah, I see it's a sunny day. But there's a lot more to it than that. We can actually tell the direction of the sun by looking at the way the shadows are cast. There's a shadow here. There's a shadow across here. We can see this shadow here, which is coming from the hat. The neat thing about this hat is it's almost a sphere, and we can see the terminator of the shadow line. And on a sphere, if we can see the shadow terminator, we can tell exactly where the sun is located. So from this image and the direction of these shadows, we can tell the sun is off somewhere in this direction, and that it's not quite directly overhead. It's behind the child somewhat. Another thing that's telling us that the sunlight is coming towards us is this area of exposure. Okay? What's different about this area of exposure is that there's some kind of fogginess here. And what this is a camera lens flare. And what a lens flare is when sunlight comes in to the lens, sunlight comes directly into the lens, it will reflect back and forth between the various elements of the lens. And usually a camera lens will have multiple glass elements to it. And those have glass surfaces and spaces between them. And sunlight will get in there and reflect back and forth, creating this kind of bloom of illumination that fogs up the image. People tend to not use lens flares as much as possible. Cinematographers go to great lengths to eliminate lens flares, except where they want them for a specific effect. Lens flares were used extensively when they were first available in CG, to the point where they became incredibly cliche. So I encourage you probably not to use lens flares, which are available in most commercial 3D rendering software. Unless you want to use them to very subtle photographic effect for a very specific reason, such as you want people to know that the sun is in front of the camera. If you do have the sun directly in the camera, which you may, that would be an appropriate time to use a lens flare because it is a photographic reality. Other things that are interesting about this image, if we look over here, we can see there's kind of a greenish tinge. And we could also see that the face is lit right up under the brim. Okay, so we can draw two conclusions from this. One conclusion is we can draw that over on this side of the child there's something green. Looking at the background, we can probably guess that it's grass or bushes or something, and that the sunlight is bouncing off of that grass or bushes or whatever, and then filling up this side of the face. Okay, we notice this doesn't feel blue, it feels green. We notice that on top of the cap, it does feel blue. Well, that makes sense, and confirms our suspicion that there's probably a blue sky, and therefore the fill light in this side of the cap, in the non-directly illuminated side, is probably light coming from the blue sky. And if we look at the front, this face, if this was sunlight from the back and just blue sky filling it up, then there should be a really soft shadow across here, shouldn't there? But there isn't. There's bright illumination here. And under the neck as well, right up under here. This indicates that the sun is coming towards us and it's hitting something behind the camera and bouncing upward onto the face. So it probably means that behind the camera there's a large surface, which is the color of light that you see here, which is kind of neutral. So probably a white or grayish surface that is reflecting light back up so that it fills in even up underneath the brim of the cap. Additionally, if we look here and here, we see light transmission, which in CG we refer to as subsurface scattering. Subsurface scattering is something that needs to be used very judiciously. You'll notice here that the subsurface scattering isn't even. And also over here you'll see that there are areas of brighter and areas of darker. That's because the ear is not all one material. It has cartilage, it has fat, it has skin, and there's probably some veins and things in there. And each of those has different densities, allowing different amounts of light to transmit through the material. One of the biggest mistakes with subsurface scattering, and especially with human faces, is to just put subsurface scattering on the face and allow it to treat the whole face material as though it's one material of one density. And that's when you get heads looking like they're made of wax, because obviously like a waxed candle is one density and one material, whereas faces have layers of skin, layers of fat, layers of muscle, layers of cartilage, which all scatter light differently. So in order for subsurface scattering to be really effective, you really need to take that into account, and you need to paint maps that are going to allow subsurface scattering to treat different areas of the flesh as though they have different density, and then your scattering will start to look and feel right. That's just an aside. Okay, here's another exterior image. We can move through this one fairly quickly. If we look at this image, the first thing we'll notice is that it's very softly lit. There's no hard shadows, and it's cool. The second thing we're going to notice is these reflections on the water where we can see sunlight. So we're going to draw the conclusion that this is a clear sunny day, and that for whatever reason the sunlight is not getting to this area. It's shining onto here. And we can see if we look at these pilings going to the water, we can see that the sunlight is only on the left side. So we can tell that the sunlight is from the left, the skylight is overhead, and that something is in the way of the sunlight getting to here. And in this case, we can see that the beach rises in this direction. And the fact is actually that there's a hill over on the left-hand side that's occluding this area from direct sunlight. Okay, here's another interesting image. Sunlight through foliage. Okay, what I really like about this image, here I'm just going to push this up a little bit so we can see the bottom of this image. What I like about this image is that it has overexposure. This image was exposed to get a lot of detail underneath in the shadowed area under the foliage on what's obviously a very clear sunny day. You can see the blue sky in the background. You can see the direct light coming through. You can also see that these shadows are not totally sharp. They're a little bit soft. So, one of the common errors in CG lighting is making the mistake that the sunlight is the same as something like what we call a direct light or a distant light. It isn't. The sun is a volume. And because it has size, it means that its shadows will soften over distance. And that's very clearly shown here. This is direct sunlight shadows, and they have softened over distance. There is no such thing as a light source that creates shadows that are completely sharp. In reality, that light doesn't exist. In order for that light to exist, the light would have to be an infinitely small, non-dimensional point in space, or just a bunch of parallel rays, such as a direct light or distant light. So you can take a point light, you can put it really, really, really distant so that the light rays are almost parallel, or you can take a direct or distant light and use that. And they'll behave the same. They'll create shadows that are about the same size as the object that's casting them, and those shadows will be completely sharp and they'll be completely wrong. For photoreal lighting, the quality of the shadows is crucial. If you're doing non-photoreal lighting, well, all bets are off. You do whatever you want based on your aesthetic vision or the render speed requirements you have or whatever. That's fine. If you're interested in doing lighting that looks and feels real, however, the quality of the shadows is crucial. Okay. But I was pointing out the overexposures here. And these overexposures really make this image feel like it's a very bright day. Even though they're tiny, they're not very common. They exist in here. And they underscore exactly how bright it is outside. Sunlight is really, really bright. As an example of this, one time when I was actually in lighting in stagecraft technology school in college, we took every single light in the theater and we focused them onto a single area on the stage, and that was about 150,000 watts of light. And there is a vent up in the top of the stage. At midday you can open it so the light will actually shine down onto the stage floor. So we did this in experiment to see if we could overpower the sunlight with all of the lights that we had, all of the wattage that we had available to us in the theater. And at midday, when that sunlight shone onto that stage floor, it cut through those theater lights like butter. You could absolutely clearly see that the sunlight was maybe 100 times brighter than all those lights. And that's very interesting because to us, inside that dark theater, when we turned on all those lights and pointed them at the floor, we're like, holy crap, that's so bright. That's got to be brighter than the sun. But it wasn't even close. That's how bright the sun is. Okay, here's where we start to get into a discussion of the color of, especially the color of sunlight and skylight. All right, these photos show some really good examples. This is, if you look at this, you could say this is either sunrise or sunset. And it's interesting. I ask my students when I show this image, what do you see here? What time of day is it? What's the environment? And most people go, well, that's sunrise. And I say, well, how do you know that's sunrise? And they're like, well, I don't know. I'm like, well, it could be sunset too. And they're like, well, yeah, I guess so. I mean, the shadows are really long, so the sun's low. It's got to be sunrise or sunset. And they say, nah, I think it's sunrise. And the fact is, it could be either sunrise or sunset. The interesting thing is that it is sunrise. And most people looking at this image get that. So there's something intuitive going on here that I haven't even been able to sort out yet that tells people this is morning rather than evening. And you know, some of the things we've discussed is, well, maybe in the evening there's been a lot more cars and there's a lot more pollution in the air, so maybe the quality of the light is different in the evening. Maybe in the morning the air is clear and clean, so the light is less amber. That could be it. I don't know for sure. What is really interesting is if you look down on the snow, especially down here, you can really start to see how blue the skylight is. Okay, here's another snow image. This one is particularly interesting. I have a couple of images in this series. What's interesting is you may look at this and say this is overcast because the shadows are all very soft. So it's an overcast sky, there's no direct sunlight. If you look closely though, you'll start to see, you can really see the shadows of these things. And on the shadowed side, you can see that it's very blue, as opposed to the unshadowed side, which is very white. Okay. If you see blue light on white snow, you must know that there's something blue nearby, and it's so large that it has to be the sky. But if it was just blue skylight, it would be blue all the way across. But it isn't. It's blue on one side and it's white on the other side. Now let me show you another picture I took of the same area about a half an hour later. Let me just go back and forth between those. Same piece of ground, about half an hour apart. All right. So in this image we can see two main things. First of all, there's no blue left, and also a lot of the form, the shape of these bits and pieces, these snowballs on the ground, has vanished. Okay. The reason is this. In this image, what had happened was a front of clouds was coming in, and it had covered up the sun, and it was about halfway across the sky. So this half is cloudlet, and so that's the left half, and the right half is blue skylit. What's really interesting about this is these are both very large light sources, so they both create very flat, very soft shadows, except that you have blue color coming in from one side and white colored light coming in from the other side. This creates a kind of a key fill shadow. It gives you definition between one side and the other, and that gives us all this shape. So even though they're both huge light sources which make very soft shadows, you can define form simply by contrasting the color from one side and the other. Whereas when we go to the same color from both sides, all of a sudden we lose so much of the form. Shape is defined by contrast, either contrast in light intensity or contrast in light color. Okay, again, here's the picture at the beginning with the skyline on one side and the cloud light on the other side, so the blue sky and the clouds. And then half an hour later, so we lost all that contrast in form. And it really shows you how blue skylight is. Okay, here's another couple of images to support the amber sunlight, blue skylight theory of mine. It's very simple. We have white snow, we know it's white. By the way, none of these images have been color corrected except that one in the candlelight, which I brightened up for you. You can see that the light in here is actually quite warm compared to white. And you can see that the light over here is obviously very cool. Alright? And here's an even better one. This area is shadowed by, there's a fence over here. so we can see just how blue skylight really is. It's really darkly, intensely blue. The way to tell how much saturation, how much color saturation is in light is simply to look at the source. If you look at a canary yellow wall, you know that the color of the light coming off of that wall is canary yellow. How much of it is a different matter, but you definitely know the color. Another interesting thing about this image is you can see on the back side of this foliage, as you can see, there's some illumination. So the sunlight is coming towards us, it's hitting a wall that's behind the camera, and it's reflecting onto the back side of this foliage. Okay, moving on. I'd just like to look at a couple of images and discuss the concept of silhouette. Silhouette can be a very powerful lighting design tool. What it does is it allows you to simplify the information that your audience is receiving, your viewers are receiving. In this case, we have a very dark outline and then a sky. And then even more so, we have, this is actually a mountain in the distance, this is Mount Baker, and it has clouds over it, and behind it the sun is rising, so it's created this halo of clouds. This immediately draws our eye to the center of the image, where there's this greatest contrast between bright and dark. Here's another image that shows silhouette in a different way. Now what's interesting is, if this image was, this is inside a room, if this room was fully illuminated, you might notice the pumpkins on the table, and then you notice all the other things in the room, and it would be a fairly busy image. But because of the nature of this image, your eyes probably immediately go to this face, which is the brightest, and you notice it, and then you probably notice these second, and then you probably notice this third. Okay, this clearly shows how composition can direct the eyes of the viewer. You can use composition to have your viewers look at specific areas of your image in the order you want them to look at. And this is an example of using silhouette to cause that to happen. We can also see that there is a radiance or radiosity bounce light happening inside here because we can't see the light sources directly, yet we still see light. These are all candle lights inside here. Okay, here's one of my favorite images to look at. This is another image where I show it to my class and I say, how does this image make you feel? And invariably the response is, well, this is very bright, it's cheerful, it makes me feel great, it gives me great energy, I love this picture, just feels really great. And that's a very natural response. What's interesting is the psychology behind the response to this image. Right? People look at it and go, oh, it's such a beautiful day, of course it's going to make me feel great. But there's much more to it than that. If I took this tree out of the equation, this would still be a beautiful sunny day, but the image would not feel as energetic. And there's a number of reasons for that. One is the contrast between the orange of the tree and the blue of the sky. This contrast gives real energy to an image. Contrast equals drama. Always, bear that in mind. And that means contrast in intensity, in color, in subject matter, in motion, in camera angles, in anything. Contrast in an image gives it greater dramatic impact. And this image has good dramatic impact because this color is complementary to this color. And by complementary, what I mean is that if you look at a color wheel, it is on the opposite side of the color wheel. If we look at this color wheel, for example, we'll see that the orange of our tree is about here, and that the blue of our sky is somewhere over here, so they're close to opposite. And colors that are opposite each other on a standard color wheel are very attractive together. Note that this is an RGB color wheel, so this takes into account red, green, and blue, which are the primary colors of light. Don't mistake that for the red, yellow, and blue color wheel that are the primary colors of pigments. And we'll be dealing with the issue of understanding pigment colors and light colors in a different section. So the contrast between colors is one of the things that adds nice drama to this. The fact that there are, basically all of the colors of light add, and then the contrast between the directly illuminated and shadowed areas is very nice. You can clearly see the cool light in these areas, and that adds up to a nicely composed, dramatic, and fairly powerful image. Here's another brightly lit sunny day image, and I wanted to discuss translucency in this picture. If we look at the leaves, we can see that they're translucent. Light is hitting them on the back side, and it's getting through. So translucency regards the partial transmission of light through a material, and this would apply to any thin material like paper or a bed sheet hanging out on the line to dry, or a lot of curtains are translucent and show shadows. And this is really the same thing as subsurface scattering. And the main difference between translucency and subsurface scattering in the world of CG is that translucency for us applies usually to objects that are a thickness of one polygon, and they show a shadow through them, whereas subsurface scattering usually applies to objects that have some depth to them, such as human skin or a candle or a glass of milk or any one of those other cliche items that subsurface scattering is used for. But understand that in the real world, light transmission is just light transmission, whether it's through clouds or milk or flesh or wax or leaves. It's all the same function. What neat thing about this image is that we can see that the light is transmitting through the leaves, and then that diffused light is acting as a light source to illuminate these parts of this sweater. So we can see these bright highlights, underlighting, that's coming from the translucent light being transmitted through these leaves under here. You can actually see it under here as well. Okay, I'd like to conclude this section with a short look at volumetrics. Volumetric lighting is something that's used not incredibly frequently in CG, but there are calls for it. Volumetric lighting in CG refers to creating a kind of a particle looking volume inside a light beam. For example, if you're in a smoky bar and the stage lights are on, you can see the smoke drifting through the light, but you don't see it anywhere else. This is different from real world volumetric lighting, because in the real world there is this fog exists all through the area, and the reason why you see the beams is because those areas are more, those particles of water, they're water droplets, are more brightly illuminated because that's where the sunlight is getting to, and the areas where you don't see it so much is because it's shadowed by these trees. In CG, we only calculate the volume where the light beam is, and the reason for that is, we use the rationale that, well, if you don't see it, then why render it? And that's pretty good rationale because volumes are very expensive to render. In general, in CG, it's a good policy that if you don't see something, you shouldn't take the time to create it or render it. Here's another shot looking up, and this is looking directly toward the sun. We can see the volumetric streaks. And then here's an example. This is looking in the other direction away from the sun, just to show you that the entire area is filled with fog, and that the volumetric streaks come from only where you see direct sunlight. Notice, however, that the shadows are, for sunlight, fairly sharp. So these particles will be diffusing the light somewhat, and in fact you can see highlights of diffusion around here. One of the things that's interesting about volumetric streaks is that because light is hitting water dropules inside these areas, the light diffuses outwards. So these areas of illumination actually become light sources themselves. So where there's a sunlight shining fairly direct light through, there's also now a secondary light source. This becomes a light source and it's spreading this beautiful soft light. So you see these soft glows that are coming from these volumetrics, which are now themselves light sources. So there's two light sources. Well, there's three if you don't. There's the sky light source that's filling in all this stuff. There's the direct sunlight that's shining on the ground. And then these volumetrics are now a third light source. So they're a volume light that is emitting light outward into the scene. And you can see those highlights. Okay, so that concludes this photographic examination. It is my hope that you have a far greater understanding of light and shadow in the real world than you previously did. And I'll see you in the next section.